It is my privilege, as the Commissioner of the Connecticut Department of Transportation, to introduce this presentation of the New Haven Harbor Crossing Program and the striking new Pearl Harbor Memorial Bridge, the largest transportation infrastructure program ever undertaken in the state of Connecticut. I'm proud to say that the Pearl Harbor Memorial Bridge has won 17 awards for excellence, including America's Transportation Grand Prize Award. Over 10,000 dedicated professionals were involved in delivering this nationally significant signature bridge and highway program. As residents of Connecticut, we should all take pride in the people and partnerships that work to build this world-class project. I hope you enjoy this fascinating account of the new Q Bridge.
This is a story about one of our country's largest, most complex transportation projects, the I-95 New Haven Harbor Crossing Corridor Improvement Program, also known as the Q Bridge Program. Spanning a generation of planning, design, and construction, the Q Bridge Program brought our nation's busiest roadway into the 21st century. The Connecticut Department of Transportation and its federal partner, the Federal Highway Administration, are pleased to offer this historical documentation of the Q Bridge program as told by the people who planned, designed, and constructed the 7.2-mile corridor, which includes the signature Pearl Harbor Memorial Bridge, the Q Bridge. Come behind the scenes and listen to how the program was designed and constructed. It is a story worth telling. New Haven was first settled in 1638 when the only way to cross the harbor was by boat. It was a time when oystering was a thriving industry. Later, steamboats transported people from New Haven to New York. As the city grew, two bridges were built, one that crossed the Mill River on Chapel Street and another that crossed the Quinnipiac River on Ferry Street. Eventually, the first Tomlinson Bridge was built across the harbor in 1797. The present-day Tomlinson Lift Bridge serves U.S. Route 1 and is actually the fourth iteration of this crossing. After World War II, President Dwight D. Eisenhower was convinced that a national system of roads for automobile and truck transit was necessary for national security as well as for the economic growth of the United States. On June 29, 1956, he authorized the Federal Aid Highway Act, and so began the construction of the interstate highway system as we know it today.
A road program that will give us the types of highways that we need for this great mass of voted here.
2 years later, in 1958, the original Quinnipiac River Bridge was completed, carrying 3 lanes of traffic in each direction across New Haven Harbor. At the time of its completion, it was one of the longest steel plate girder bridges in the nation. With an expected lifespan of 50 years and a design capacity of 40,000 vehicles per day, the original bridge was considered a marvel. However, by the mid-1990s, when the bridge carried over 140,000 vehicles per day, more than 3 times the volume for which it was designed, the Connecticut Department of Transportation took steps to repair or to replace the original bridge.
During that time, the Q Bridge was costing more and more money to maintain in a state of good repair. The bridge was old, it was carrying much more traffic than it was ever intended to. We kept having to do projects to repair it.
The previous bridge, as I understand it, was actually a record setter for its type in the country when it was built. So, I mean, it was a pretty significant achievement. It lasted a long time. It was too narrow, and it was falling apart.
It was just under capacity towards the end and deteriorated to the point where we had multiple emergency repairs that had to be performed.
Technical term was structurally deficient and functionally obsolete. So we needed to look at either a replacement or a long-term repair for the bridge, and the decision was ultimately made to replace the bridge.
It had to be removed in a very specific sequential order. The contractor hired an engineer to design a demolition plan, and that had to be closely followed. We had to perform the demolition in accordance with all the environmental permits from the Department of Energy and Environmental Protection, from the Army Corps of Engineers, to make sure that we weren't dropping material down into the waterway. We had to hang nets underneath to catch anything. We had to coordinate very closely with the U.S. Coast Guard because it's a navigable waterway. We had to keep the channel open. There were a couple of times when we removed the steel over over the channel where we had to close the channel for safety reasons. There was one pier, pier number 13, that had to be removed to a significant depth below the waterway because of a widened channel, and that had to be blasted out of the water.
It was important to the city that a signature bridge be built in New Haven. To the casual observer, the Q Bridge is probably the largest architectural feature that you can see in the city of New Haven. When the department was considering what type of structure to put in, the city of New Haven weighed in. They were pretty adamant that they wanted to have a significant bridge, something that was recognizable.
The job itself started in 2001, and I was part of the project during the design phase. To be honest, these jobs start out with a white sheet of paper. We had to put a new bridge on top of an old bridge in the same footprint and keep 3 lanes of traffic in each direction. So that was the fundamental challenge of this project.
There were some challenges to the site. New Haven Harbor is a busy place.
There's a navigational channel down below. Certainly need to keep minimum clearances for that. So the bridge depth or the girder depth couldn't go too deep. The elevation of the highway had to be maintained at the midpoint of the bridge. And there's a nearby airport, Tweed, New Haven. So between trying to not go too deep into the navigational channel and not raise the profile of the bridge too much, the designer looked at what they call an extradose bridge, which was fairly common in Japan at the time.
And what basically happened is it pointed towards this new technology of an extradose bridge that could combine a medium span bridge with a short tower and fit in this thread the needle footprint that we had to deal with. We decided what we call balanced cantilever cast in place construction with the form traveler.
It's a relatively rare structure type, although it's becoming more and more common.
Instead of all the load being taken up by the cables, which happens on a cable stay bridge, live load is taken by the cables and the dead load is taken by the rest of the superstructure.
Basically, it's a hybrid of a stay cabled structure and a traditional segmental box girder structure, but basically the towers are shorter, so therefore the stays themselves are flatter, so it's more of an external post-tensioning, but that's the very definition of an extradose bridge, is to have that inclination of the stays be flat.
This meeting was going to be really important, so I said I'm going to take these hand sketches that I had done and presented it to the broad audience. We were kind of confident they liked what we were presenting, and we got a resounding yes to design 2 bridges, concrete and steel, to put out to bid. We recognized that because the fatigue cycles were less, we could raise the allowable stresses in the cable to a higher level, and that has now been adopted by current codes.
Decision was made, yes, we're going to go with an extradose cable stayed bridge, and we proceeded with the final design and to build the bridge.
I couldn't imagine any other bridge there right now. It just fits. It was decided that we wanted this really dignified approach, which is called the anchor pier, but we wanted it to be a monumental approach so that if you're coming from either direction, you know you're hitting something special. It's kind of reminiscent of the ship smokestack, and it gained traction, and I know ovals are hard to build for the contractor. So I developed an oval, but it's really a compound curve made up of 2 circles at the end and 2 circles that connect it. And you can really reinforce those ends really nicely and get good seismic strain.
The Connecticut State Legislature designated the bridge as the Pearl Harbor Memorial Bridge. The cables, as they come down, sort of look like sails in a way of ships, so it has sort of a nautical theme to it.
When you have a nautical theme like Pearl Harbor, you tend to gravitate towards things that are ship related. Another thing, if you look at the bridge closely, you'll see these reveal lines up and down the tower legs, and if you didn't put those in, it would look too massive and stark. So those really create relief to the eye and kind of make it on a more human scale. The state of Connecticut wanted to recognize the service of the veterans. My dad was a World War veteran and landed at Normandy, so I felt kind of a closeness to that ideal. We even went in terms of the size of the lettering. So that captured what we were trying to present.
The coordination necessary to deliver a bridge of this type with an adjacent highway-to-highway interchange presented a tremendous amount of complexities.
Reconfiguring and redesigning the interchange was really key to the success of improving transportation throughout this corridor.
The interchange next to it has 200,000 cars. If we didn't have to maintain safe travel for all those cars every day, we could build this project much faster. And of course, the impact of that is it took more time.
So you didn't really see any traffic flow betterment at all during the approach work as much as you did once the Q Bridge and interchange was done. That interchange is what received all the vehicles coming off and going onto that Q Bridge into an interchange highway system. So the approaches on the west side had to be done concurrently with the approaches on the Q Bridge.
We need to build the bridge without being in the same footprint of the existing bridge, so we need to keep the foundations away from the existing ones. So all of those sort of factors weighed in as the design sort of developed and they settled in on the extra dose concept.
It was really maintaining existing lanes all the time during high peak hours, and the challenge was to figure out how to get everything all built while maintaining those existing lanes, and then just have that all work from what we had determined in our construction staging to say that, okay, we laid that out and we could actually see it all happen from up there. It was really, really great.
We were introduced into the 4D model during the design phase of the interchange project. It's basically a 3D model that you put the element of time and schedule to, which creates a 4D element or product. And we thought, what better place to use it than the interchange? It was a very complicated project as far as staging, reconstructing of an interchange within the footprint of an existing interchange. So we thought this 3D 4D modeling would be really beneficial. We introduced it to a mandatory pre-bid conference, and we introduced this modeling program which showed how the department saw this project getting built. And we also notified the contractor that we would make this model available to the project team. I think we had identified 8 additional conflicts that we didn't see during the design phase for the interchange that we did identify once we put this model into place. So right there we saw the benefit. And the first time we used it was during the flyover structure that we put in contract E2, where we had to stop traffic on 95 and 91 in order to erect these tub girders. We had 20-minute stoppages to do this, and just to capture how it would flow minute by minute. Once the project was underway, we introduced it to the contractor a little at a time, and every time they would have an idea, we'd say, well, let's put it to the model and let's see how it reacts in the modeling program. And we're like, you know what, maybe this is kind of a beneficial program, and we used it quite a bit after that. There was a structure that we had to demolish 18 inches away from an existing historical building. We used the modeling program and really combined it with scanning to try and identify conflicts, and it worked out really well. But we also use it heavily with our public info relations.
DOT has some animation to show you what this is going to be like when it's over on Saturday morning.
We have it as part of our presentations. We use it on the website to show people stage shifts and things like that. But when you put a visualization type of model to it and show what the shift is going to be, it really gets the traveling public to get a better idea of what's happening.
Workers broke ground for the Pearl Harbor Memorial Bridge main span in 2010, building on a foundation system begun in 2008 under a separate project. From the beginning, the construction program demanded the highest level of professional cooperation and creativity from many public and private sector contributors.
We worked off of temporary trestles, so you had to design those trestles to withstand the loads of this very large and heavy construction equipment.
The main span is about 515 feet across the channel, so we couldn't interfere with any of the channels because of the navigation. But between the shoreline and the tower pier, that's not a navigational area, so trestles were necessary between the shoreline and the tower piers. The trestle was founded on 24-inch pipe piles that were driven down to bedrock Bedrock widely varied from one side of the channel to the other. It was only 40 feet or so down to the east side of the channel, where it was about 180 feet down on the west side of the channel, so it really dropped off significantly. So the pipe piles were then driven to bedrock. There was a girder steel superstructure that was built on top of the pipe piles, and then timber decking went on top of that. The contractor used concrete decking at heavy lift areas and turn areas of the trestle.
The foundation or the supporting structure of the bridge is based on drilled shafts. And a drilled shaft is a circular column of concrete that is socketed into the rock below. And so that foundation, that force from the bridge transfers from all the way down in the towers into the foundation to the rock below. In particular, we used something called an oscillator. What an oscillator does, it takes a steel tube, which is our steel casing, that becomes the form, if you will, for the drilled shaft, and that rotates back and forth, not fully in a circle, but oscillates back and forth and basically screws that tube, if you will, into the rock below. And then it will excavate out to the rock, to solid rock. And then what we would do is fill up that steel casing with concrete and reinforcing steel, and that would form our drilled shafts.
You're digging out what are called drilled shafts, which are basically reinforced concrete piers that go down all the way into the bedrock.
So they determine the elevation of what we call weathered rock and then competent rock. And then that information is brought to the designers, so then they determine where competent rock begins and how far you have to drill the drilled shaft casing.
Some of the foundations are as deep as 180 feet down below ground level. We have special drilling equipment that sits on temporary supports. You know, you can't really see what you're doing because you're down underneath the water. That can be a very challenging process.
We had a sleeve of steel that was 3/4 of an inch thick, that every time they would auger out, that casing would follow through into the hole.
Then you have to seed it into rock to make sure you don't get any washouts. And then you bring different equipment in to excavate the rock socket. The rock socket goes anywhere from 10 to 30 feet down into bedrock. Different types of equipment were used with that, some with water pressure, some with hydraulic energy to make that happen. Once the rock socket is put into place, and it has to be totally clean so you get a bond between the concrete and the rock. They use various methods to clean it out to make sure it's perfectly clean before you proceed any further. You have a prefabricated rebar cage. The rebar cage has CSL tubes. CSL is for cross-sonic logging to check the integrity of the shaft after it's poured. After you put the rebar cage in, then you do underwater concrete. It's a TREMI method of pouring concrete, where you start at the bottom, you pour the concrete in the water, and you proceed upwards. So we did that with all the shafts on the entire project. At the top of the tower piers, the first segment on each side of the tower pier are built under traditional construction methods, and they serve as a platform for the rest of the work. So first you build the pier tables at the top of the tower piers, and then the form travelers can be used.
And a pier table was a very large piece of concrete, about 40 feet long, and that allowed us to start as a starting point for the cantilever process.
Because we had a concrete segmental bridge and it was cast in place as opposed to a precast, form travelers were the conventional method that most of the contracting community would use to build a segmental bridge.
We had 4 form traveler assemblies being used concurrently, so there's 2 at each tower pier. So what you do is you proceed out from the tower pier with 1 form traveler towards the middle, and then the next pour will be towards the back or towards the anchor pier. Form travelers enabled us to pour about a 14-foot long section of superstructure at one time.
It's a series of trusses and steel frames that basically is a formwork and supporting structure for the wet concrete. So as we had cast these segments up in the air, this form traveler would hold the wet concrete and be anchored to the previously hardened concrete.
It's a constant process. So every time we pour a new segment, we're checking before the pour, we're checking the geometry after the pour, we're comparing notes with the contractor to make sure they're getting the same numbers that we are. And it's just a constant, ongoing process the entire time. And as you get closer and closer, it gets a little nerve-wracking because you want to make sure that you're coming into the right spot. And sometimes the bridge doesn't behave quite like the computer models say.
We're always checking geometry to make sure it's headed straight and it's at the right deflection. We were within 1 to 2 inches in elevation of where we needed to be when we did that, which is very easy to make up. So it was very successful in that regard.
And the trick is that every time you cast another piece of the bridge, another segment, you have to make sure that the geometry of that overall length of those cantilevers and the geometry of the next segment that you're placing is such that when you end up coming together with the cantilevers from the other side of the river, that they meet in the middle properly. In the end, when you come in, close like you were expecting to, that's a great feeling.
When this bridge was designed back in the early 2000s, we knew that we were going to have a signature bridge. We had decided on using aesthetic lighting to light up the towers, light up the cables. Pretty common in a lot of large bridge structures. And the key benefit of going with LED lights is you can change the colors. So the original stakeholder group did have some concerns with changing colors on a memorial bridge. Birds could fly around the bridge because they're attracted to large amounts of light. So from environmental standpoint, they thought that using the color would be a better option and we could use softer hues during the migratory bird season. The LEDs, I think, really showcase it based on some of the feedback that we've gotten from the public to date. They really appreciate being able to kind of change it up, use some red, white, and blue on July 4th or that kind of thing, and I think that people really enjoy it.
You've got people that are working out there in all kinds of weather. I mean, from freezing cold New England winters to hot and humid summers and everything in between. Sometimes it's windy and sometimes it's raining. And
well, I think it was a real collaborative effort between all the parties involved. Certainly the Department of Transportation took the lead on that. They had to keep plugging away day or night through all the months of the year, through the winter months, and we had some really rough winters during that time frame.
It's a very big sense of accomplishment. This job is a very big success from the perspective of everyone working as a team. And again, that could come across as a cliche sometimes, but everyone worked together for one common goal.
Everybody out there takes a lot of pride in what they're doing. So, whether you're a laborer, whether you're an iron worker, you're an engineer, an inspector, I mean, all the way up and down the whole range, you've got people out there that feel like this is an important project, they understand that, and they put a lot of time and effort into it. So the work ethic is pretty amazing.
We can always come back and drive across the structure and say, hey, I had a hand in that, or we built that.
We got the bridge open when we said we were going to get open. We met or exceeded all project milestones as far as the opening of the northbound bridge, the opening of different ramps, the opening of the southbound bridge. And we were able to do that in keeping under the project budget, which is really quite an accomplishment. So that certainly is something to be very proud of.
When you saw the way things were coming together, it made you even more proud that we were doing a good job.
It's extremely gratifying to see a project that you worked on during design development, then you helped oversee it through construction, and now as we near completion, it's extremely gratifying.
We did a project of this size and magnitude and notoriety, being the first of its kind constructed in the United States, bringing in that sort of level of national exposure and national experience into it, and really assembling a team from around North America to come in and build this job with everybody of the mindset that we're going to get this job done, we're going to get it done on time, and we're going to try and get it done within budget, with a quality structure. I think everybody had a stake in the project. And I think that's really probably one of the key pieces to the success. Just watching a team work like that to make a success of a large project like this, and to really sit back and watch and then learn from and then carry forward into any sort of future projects.
One of the major drivers with the project was schedule. It's always been schedule driven. We wanted to get the job done as quick as we could, but reasonably.
The contract itself was very long. It was 6.5 years. The scope of the work was enormous.
And it had to do with the right people in the right places making the right decisions when they needed to make them.
We all came together as one for this one amazing project, which I call a career project. That I'll carry with me for a long, long time. It was a really great thing to happen.
It was a pleasure to work with a high number of talented people from the state and the Federal Highway Administration to all the consultants and the contractors I work with. But the thing that really struck me is a couple of times during the course of this contract was the honor to meet and talk to the Pearl Harbor survivors. These are members of our greatest generation. This is my dad's generation, and I couldn't have been prouder to be part of a project that built a bridge in their honor.
This is a great project. We've learned a lot of lessons about how to get these things done and how to rebuild our economy. This is the demonstration project. There are many, many, many more to come in the coming years.
It's got the lifespan of 100 years. So when your grandchildren are having grandchildren, they will be here riding over this bridge for the next 10 decades. So when you think about that, we're going to actually be maintaining our bridges in better conditions for the next few generations.
It is, as the governor has pointed out, the largest project in the history of the Connecticut Department of Transportation. And in the end, almost 9 out of the $10 spent on this project came from federal funds. It's also an example of what is possible if we commit to investing in infrastructure, if we begin to be a nation again that builds and not just consumes.
It's what it symbolizes and what the future of our economy. This is an anchor of that, jobs, putting people to work. So many things that really capture what the U.S. has been all about.
The Q Bridge program takes us from the past to the future, linking what came before to what will be. Thanks to the dedicated efforts and talents of many hundreds of people, that future shines brighter today.